All right, folks. Please find a seat and sit down. We'll get the lecture started shortly. All right. Can you guys all hear me correct? Okay, in the back? Or is this too low? Hello, hello. Is this one better? All right, guys, let's get the lecture started. Thank you for coming. Please find a seat if you haven't already. Can those who in the back hear me okay with this microphone? Okay, perfect. All right, yeah. So first thing first, for those who celebrate it, Happy Lunar New Year. It's a big holiday. So in the spirits of that, we're gonna have a kind of light lecture today. So likely we're gonna end up earlier and then you're free to go earlier. So yep, today we're gonna talk about interrupts and NVIC, the nested vector interrupt controller. Before we start the lecture content, a couple announcements. Okay, so first is the lecture note worksheet. Please remember to put your names, unique ID, or unique name, and also the UMID on the sheet. Next time we will have like a designated area on like top corner or something, so that everyone don't forget. So yeah, for those who, I don't know, draw like a PCAT and PDoc instead of writing the names, please come find me after the class and then claim your worksheet. And for those who you think you turned it in or but didn't see it on the Grayscope, also come to me afterwards, and then we will figure it out. We also have like a couple unnamed worksheets. So that's that. Besides that, the homework 3 is released. It's due this Friday at the usual time. And exciting, the midterm one is coming up in about 2 weeks, well, 1 week and a half. It's at the Friday 7th on the February. It's going to happen at 4:30 to 6:30 p.m. and at those 3 rooms. They should be really connected to each other. You will get like a assigned classroom, or I'm not sure, maybe based on like a first come, first serve. But you will be assigned to like a designated classroom, and then sitting there. We're going to have like 1 seat in between being empty. And so yeah, the TAs and GSI is going to sit in the hallway in case you have any questions for us. I'm also sitting there in the hallway. The topics to cover, pretty much the lecture materials until this Thursday, basically after the interrupt and NVIC. Yes, already questions?
So what content will you give us to prepare for the
Yes, good question. So we will have, we'll give you at least 2 previous midterm 1 exams as the practice. We'll probably give you 3, but at least 2. And then we will have next Tuesday's lecture. Yeah, I mean, depends on which day you guys want. Do you want Tuesday or Thursday as one of the review lecture? We will go through some of the previous topics we covered, and then maybe some practice questions that's in the practice exams, if you guys feel more like it. So currently set to be next Tuesday, but if you guys feel like Thursday is better, either way works with me. So any other questions so far for the announcement? No? Okay, perfect. So we will post the practice exam this Friday-ish, like hopefully after the homework 3, so that people don't get distracted too much. And I think for you guys, a week of practice time is more than enough. So yeah, don't overcomplicate it. We're not going to trick you. It's just a midterm exam. You have a ton of stuff later in your life that's much harder than this. So. Yeah, components of the day. So today we're going to talk about servos. Who have used servos in your class? In any other projects? Wow, quite a lot of you. Nice. Good. So basically, there are like special types of motors. It's a rotary or sometimes linear, but usually rotary actuators that allows for precise control of the position and sometimes speed and acceleration. You will see on like the top left figure here, you usually have like a DC motor inside of the little package, and then a potentiometers that's kind of like an internal feedback, like a built-in feedback system that knows the current orientation based on the current reading of the potentiometer. So it will keep the angle at like a particular position. Even if you like overshoot or turn it around, it likely can adjust it back. And it's a very convenient three-wire interface, one of them power, one of them ground, and leaving the next one basically one-pin connection, one-pin control to a certain extent. It's controlled through PWM, the pulse width modulation. I'm not sure if you guys worked with this in previous classes, but you certainly will in the later part of this class. This signal will tell the servo what angle to be and etc. Depends on the types of the servo. This type of actuator is very nice for robotics controls because it's precise at the location and orientation. And typically there are two types of the servos. At the bottom shows standard and continuous. Standard is basically the rotating motor that rotates within a fixed range, 0 to 180 degrees, typically. And for continuous rotation servos, it can be rotates continuously in either directions. And the PWM signal control basically tells the speed and direction of the rotation rather than the exact position. So yeah, that's that. I think you haven't, for those who haven't used it yet, don't worry about that. You will likely use it in some format, either in final projects or later on for this type of easy to interact actuators. Cool. Oh yeah, there's a quick video demo. When you combine the servo with a IMU, which type of interactions or which type of controls you're capable of enabling. Flying a flight. Little bit on the previous lecture, I think we see some of the questions during the piazza and also during office hours. There might be some confusions around some of the signals inside of the previous two examples. So one of the question we had is, which I think is a really good question, and is why, in this case, a register that reads from this register and all writes right to this register, why we're using the p-enable, p-select, and p-write 3 goes into one AND gate and then use that to connect to the enable pin. The reason that is because basically under a write instructions, any of these register within a peripheral is only being enabled with the following conditions. First, the p-enable is high, which is a signal sent from the requester to all the completers, or from master to all slaves, indicating that whatever data currently on the bus are ready. So they can do whatever instructions it needs to be done for all the completers to know. And the second is the p-write, which in this case is more straightforward. Basically, if it's high, then it indicates it's a write instruction. If it's low, it's a read. So if it's high, that's something the D flip-flop here will typically have to do something. That's why that also have to go to this AND gate. And the third one is the p-select, which is an individual pin for each of the peripherals. So that peripheral needs to know that this is my turn to respond to all those other data on the bus and also the enable pins that on the bus. So yeah, and this is a simplified version, I think, because there's only one register, or in this case, just one peripherals. If, say, we have multiple registers in one peripherals, then, which is what this happens, which is why we essentially need to have another, the address pins to be part of that enable. Because if you think about it, we have, let's see how to do it. So on the top, we have peripherals, and underneath peripherals, there are a few registers, right, that belongs to this one peripheral. And whatever signal that's sent to that peripheral is shared by all these registers. So in this case, the p-select pin will be shared with all those that they have the capability to connect to that pin. So we need something additional to know which exactly register is needed to be the ones to be activated, which is what the p address is needed here. They have basically one bit on and off mapped for each of the register within a peripheral. And one sec. And then under each of the register, they might have multiple D flip-flops. But we don't talk too much on that. But basically, you can imagine most of the D flip-flop share the same, or at least share parts of the signal from the register. Yes, do you have a question?
Yeah. So wait, you said the P address selects registers within a single peripheral.
Mm-hmm.
What does the P selector do? It selects each peripheral, or?
Yeah, the P select ping is an individual signal to each peripheral to tell that if this peripheral should be the one that responds. And then inside of this peripheral, there are multiple registers that could be called or could be activated. And then that was decided by the address. Remembering from like the MMIO, all the registers are essentially part of the memory of the entire system. So that address tells it which exactly address that a read or write instruction is targeting at. Okay, so that's why there are an additional AND gate here for those signals before they connect to the 2 enable. Okay, I hope that part is clear. Any question on that part? Okay, perfect. And oh, yeah, sorry.
I was going to say, like, what is P adder? It's just
The P.
Like, it selects the register. Is that what it is? Or?
The P address?
Yeah.
Yeah, essentially it's like a bit-to-bit mapping towards each of the registers. You can think of this one is like a 32-bit, so essentially you have the capability to control 32 registers, and then each bit corresponding to if it's on and off for that each corresponding registers. Typically, we don't have that many within each of the peripherals. Yes.
When would the P enable be true and the P write be false, or vice versa?
P enable be true and P what?
P write would be false.
Oh, under like say read instruction, so like load basically. So they're not really storing or write anything. It's just load or read from a certain register. Then the P write will be low, and then yeah.
The P enable bit.
The P enable is set by the master or by the requester. Okay, cool. And one additional thing is asking about why the P write data connected to both of these registers, output register and also the motor. The output register is pretty straightforward because that's the data it's going to be eventually, push out of the pin. The reason for it also connects to the motor is because like the GPIO mode register is because, again, back to like the MMIO, because all the registers are essentially from the IS of the processor, a piece of memory inside of its memory IO map. And so that register needs to be write into or like load the value into in order to set the mode of this GPIO peripheral. So any registers that needs to be updated in order to do something, you can think like the P write data have a part of doing it. It does not happen in one instruction, so to speak, or in one cycle for sure. So it will be like 2 different instructions. One specifically write or store values to the motor, which sets this GPIO to say output mode analog pin. And then the next instruction, or somewhere down the line, it writes another write instruction to the output register, which outputs the actual value through the GPIO pin, physical pin. Okay, I hope, okay. Yeah, no question.
How good is the abstraction of it just being memory? Because, for example, if I loaded from like a 48X and this bunch of zeros and 5, I would expect to get the higher bits of the output register, but that's not going to happen in this model. So,
Sorry, can I say one more time? You're trying to load from where?
yeah, if you're not loading exactly from one of those addresses, if you loaded, for example, from one byte higher on the GPIO out, if there was normal memory, you would expect to get the higher bytes, but in this case, it's not going to work because of the way we have set this up.
Yes, and I think generally if they are, remember from the previous lectures, they are instructions for essentially load half of the data for some of the instructions. If that's built in for that specific register, then that's legal, but in terms of if you do just by incrementing, say, 1 to it, I think it will be considered as like a bad behavior, or like, yeah. Yes?
What is the p-select for?
The P what?
P-select.
Oh, the p-select ping is, so p-select ping is a signal that sent from the core or master to all the peripherals to let them know which one is being like the chosen one. And that's like signal individually goes to each of the peripherals. Yeah. And all others, well, the p-write and p-enable are one signal goes to all peripherals. p-select goes to one. And in case, and the p-ready was the signal that come from the peripheral or from the completer to the requester or to the master. I know there's a lot of terms nowadays because we're in a very fast stage, like people are updating names, but so completers, masters, or initiators are essentially the same thing. And in our content, like completers, slave, and also peripherals, in a lot of times are kind of interchangeable in this content. Yeah. Any other question? Or, okay, we have one more.
You may have already explained this, but can you explain the 0-bit that's coming from ODR and motor to the input?
Oh, yes. Yes, for this example specifically is because the question, sorry, it doesn't have it all printed out, but the question on that one is basically ask you to control the zeros index of that, basically mapping the zeros index of the output to that output GPIO. So that's why we put like a 0 there, because that's something like specified by the question. But yeah, you could have the entire data onto one ping. Imagine, if you remember from before, we do like a serial to like serial out. Basically, you have that output 1 bit at a time, and then so they have the potential to essentially go through one ping. But in this specific case, in like a more simplified version, we just chose to have 1 bit directly mapped to the output I/O. Okay, I hope that answers all the questions we have for these two parts. Good? Okay, perfect. You guys are ready for the exam. Cool, so today's topic is gonna be mainly around like the interrupts, and if we have time, well, we're also gonna touch a little bit on like the NVIC, the nested vector interrupt controller. The idea of interrupts, like why we need to have them, is typically like doing a program, or I guess like many things in life, often we have to deal with asynchronized events. And those, for example, like applications make like a system call or some illegal instructions, like typically what happens, you divide it by 0, that causes some illegal exceptions, or like some peripherals need attention or like have completed a request action. For example, someone pushed the button. We always use the button. Someone switched the switch. That should ideally trigger something. So how do we know when or exactly like when this event happens, and how do we deal with it? Well, there are broadly like 2 ways to do the detect of the event to start with. First is called like polling. Basically, we're repeatedly poll the application or processor in every loop, and then see is there anything happening on that particular peripherals or hardware to check if anything is happening there. And if there is, then we detect this and take action in that one loop. And there's also other ways to do it, which is what we're mainly going to talk about, like the interrupt. Basically, the hardware or like whatever that piece of thing let the processor or let the main program know that something's happening, and then the main program will take action when such like a notification happens. So I think a good way to think of it is like polling is kind of like, texting with notification turned off, or like waiting for someone to reply when that someone is likely never going to reply to you. That kind of how the polling is. And to put it in more of a coding context, basically this is like like a very, very small piece of code that doesn't do much. Basically, what it does is just just do a bunch of moves and then load. And then that load, let me see, this load is essentially where we are checking the value from, in this case, a switch to see if there's an event happening here. So in this case, probably works okay because it's a very small piece of code and it's super fast. Every 3 or 4 cycles, you read that event ping one times. And yeah, no human being will be able to press the switch or button that fast. But the downside is that you can't do anything else with this program. The whole program is only there for listening to that one switch to go off. And also, if you want to do some more work here, say if we add another 100 cycles to do some meaningful calculation, then in this case, it might still be okay because it's only 100 cycle. But you see how this is going, right? Basically, if you just keep on adding stuff, this case it's only 100 cycle, which is still probably okay for most people's use case. But then you start to add a bunch of other stuff, which is much more typical for like an embedded system, like something a little bit more complicated, I guess. And then you eventually become like very unmanageable, and the whole program will have like a very, very long latency on any of the event triggering. And in this case, we're not even talking about if we have like multiple events happening, like what you do with it. Then all the latency got accumulated, and eventually, it just doesn't really work. So, yeah, become much less responsive to like the external events, especially hardwares and stuff. And as you might or might not remember from the lecture 1, the embedded system, a lot of times it's about real time. So, like one event happens, there's something supposed to happen in relatively short time on your system, so that if it's in a car, you don't crash, which is good to have. So yeah, we can definitely do better, which is why we came up with interrupts. As a word, it means break the unity and the continuity of something. In our context, it's pretty much inform a program that some event is happening, and it should breaks the execution flow at the moment. Do that and then come back. So, yeah, interrupts basically, we're going to call this a interrupt service routing, an ISR. This is typically like an interrupt service it's like a handler call or like a function call that occurs when the interrupting event is happening. And then the system will jump to, or the main program will break out and then jump to that, do something, and then come back. And you will probably imagine that normally we'll try not to do like a lot of work within each of the interrupts. Otherwise, you're going to kind of like doing all these ISR routines all the time and then the main program also gets stalled and stuff. So it's a little bit trade-off here, but usually interrupts is something that does something really fairly quickly and fairly small amount of code to be executed. Another reason is also it's kind of hard to interrupt. We will talk more about that in later lecture. We have like priorities set for different types of interrupt, but generally it's not really good to have multiple interrupting each other, and chances are you're going to run into some system exception or some errors in the memory, etc. This is good so far, right? Okay. So we have basically 2 types of interrupts. The first one is we'll call them basically the system exceptions. So it usually caused by an instruction or like a system fault. For example, like the illegal unimplemented instructions like divided by 0, or like some supervised calls, which is like an instruction in ARM architecture and like a software trigger interrupt to request service from like a higher privileged model. like imagine in your computer, you go to like supervised mode, etc. And we also have the interrupts caused by the external word or like by like non-instruction event. Typically, we just call them external interrupts, or for short interrupts for the matter, because that's the main types of interrupt we're going to have within our class. Those are basically caused from external from the core, not from the chip. So it may a lot of times caused by peripherals and stuff on the chip, on the whole board. It's not from, so to speak, outside of the code area or outside of the chip board. It's still within the chip, just not from the core. And you can say that it's kind of like a good interrupt because it gives you some events or flags to do something and to make sure program acts as it's supposed to be. So yeah, as we talked, like button push and then some of the communication protocols you will learn later. I think you see this word a lot of times, SPI, I2C, and also like, for example, the ADC channel, analog to digital converter. Whenever that conversion is finished, it also gives like a quick interrupt to let the system know, I'm ready for something, take the data from me, and then we can do some cool stuff together. Yeah. So like a quick overview here, basically, it's usually hardware, sometimes firmware, but in our class, usually hardware or peripherals generates an interrupt signal, and the core will decide, determine which interrupt fired, and then what code to execute. And then it will hold the main code execution and then run the interrupt service routine, or ISR, which is basically the function handler function that goes to for each of the corresponding interrupts. And then return the process to the original state and continue the previous code. All good on this abstract part? Okay, perfect. All right, so again, this is the simplified architecture figure of the Cortex M4 chip. And how do you think a interrupt is happened or occurred or delivered from the peripheral to the core? You can talk to your neighbors for 1 minute or so and discuss something. And you can think like, should we use the buses for that? Or if so, how? If so, which buses should we use? If not, which other type of things we should consider? You don't have to come up with exact names, but just some general thoughts on this. Yep, please discuss with your neighbor. Okay, any thoughts? Any thoughts from anyone? Or I can break the question down. So first, should we use the buses? Any thoughts on that? Yes. Think so? And why is that? I see. Okay, there are some folks think it's good to use buses because they're like, I guess, pre-built route that's already existing inside of the core. Any other thoughts? Any people who think this as well, or any other thoughts on this? Oh, I think I heard a lot of discussion, but okay. I guess people are too shy today. Yeah, I think this question is kind of getting ahead of time. So the short answer is we don't typically use buses for that. And this is mainly for the latency and prioritization issues, because like buses are designed for like general purpose data transfer. What is happening? Okay, general purpose data transferring. So delays in like, so there's always constantly stuff flowing around on the buses. So if we also put like interrupts inside of the bus, which should have like a higher priority, then it causes like longer delay times here. And the stuff we're actually going to use, oftentimes are actually just hard wires that's connected to the core. They're usually managed by what we call NVIC, which is the second part of the class title, the vector controller, interrupt controller that handles all those wires and then decides which of these interrupts should go. So yeah. I guess you guys, this is a little bit ahead of the lecture, but yeah. So the NVIC here in the middle, basically, this is like a quick overview from the top to the interrupts. Essentially, they are like we said, different type of interrupts. In the case where the peripheral interrupts happens, the IRQs, the interrupt requests. They basically send out interrupt request RRQs to the NVIC, and NVIC decides, which type of interrupts coming and where it should direct the main program to with this type of interrupt. Remembering, like each of those type of interrupts are hardwired, so they have like a designated signal to that interrupt, one number assigned to it. We'll show you in more detail later, but basically it's very fast, and the core or like the processor gets that information immediately, and it knows where that comes from because they are hardwired. Of course, like we said before, there are different type of interrupts, like the system interrupts, system exceptions, etc. They come from the cores, and also we have like what they call system tick timer, which is like a specialized timer that's built into the Cortex-M processor. It's like a simple and effective way to do like periodic interrupts, such as like delays or system timing. We're not going to talk too much on that, but that's just something in case you're wondering. Oh, and there's also the thing called like NMI, which is also from peripherals, but basically it's called non-maskable interrupts. It's a type of interrupt that cannot be disabled or like masked. You can think of it have even higher priority. It's saved or reserved for like critical events that require immediate attention. So like something hardware failures or system failures from that piece of peripherals, for example. Typically not those like events we talked about that we were designed to interact with. And so to put into context, basically, we have some program running, and then at some point, like an interrupt happened, and all of a sudden, and then we go to this table, which is part of the NVIC, the interrupt vector table, to look for which type of interrupt it's corresponding to. Remember, like each of them are hardwired, so we know exactly where they come from. in this case, it's that, and then it tells us to call the memory location at 5C, which points to a handler function, which is the ISR, the interrupt service routine, and then it does something. And after that's done, it basically go back to the main program as if nothing happened, and main program keep going on. Any questions on this high-level diagram? Okay, perfect. So next we're going to look more detail into like this interrupt vector table. So it's essentially like a data structure that contains the starting address of a exception handler, or like the ISRs, and it defines how the processor handles each of these interrupts, essentially. And this is the instruction memories we have from like the MMIO, if you still remember. Basically, at the core, we will typically want, whenever like a program starts or you reset the program, the initial stack pointer, or to be more specific, the main stack pointer will be located at 00000, and then we will have the interrupt vector table on top of that, which is mapped between the indexing in memories. This is where they store where the interrupts are. This is like a typical system on like a Cortex-M. In the lab, just for some clarification, sometimes they will make like aliens. Basically, they copy those over to a different address, like 8080000, where is the flash start. This is because if you want to, like, say, store your code for like long term, then you should, put things there, because it's whenever the power goes off, the code still be saved there, and whenever it got boot up, that's essentially the system will automatically run the same program over. But for the class, we just assume that, or like for most of the systems, I guess, we assume that whenever we start the program or whenever we reset, the main stack pointer will goes to the 000, and then the interrupt vector table will be on top of that. Okay, so this is what an example of ISR vector table look like. So it's simply a list of function address stored at the beginning of the memory, which is what we just looked at. And the ISRs is the software routine or function executed in response to an interrupt request. It contains like the code that processes the interrupt event and perform the necessary responses or actions. And the processor basically jumps to the ISR when the corresponding request is happening, and then do whatever it needs to be done. What exactly contained in an ISR, like the interrupt service routine, is something you can decide. So when something happened, you let the system do something in response. It's only those like address or numbers are preset, but you can decide what's being stored in that memory address, if that makes sense. Okay. So yeah, as we said before, beginning at the 0000 holds the value of the stack pointer, which holds some memory addresses there. And the PC program counter initialized to be at 00004, and again, it holds the value of the reset handler, which initializes the chip whenever, and then branches to the main function when the system is ready, or when the system is reboot up, I guess. Any questions on this? All good? Yeah, just notice that those, like the number there, they're referring to the address stored at that location. So you can change what's the address stored there, hence change what's the function do in each of that location. Okay. So we'll be looking up those IRQs, basically interrupt request. These are referring to the signal or event generated by, in our case, peripherals or like external devices that request the processor's attention. It's a hardware signal, so that it tells the processor something has occurred and it needs immediate handling. Each of these IRQs, each of the interrupt requests, have an assigned number. In the system, like the ARM-given architecture with up to 256 IRQs, but in the STM, like the chip we work with, have only 96 plus 16. The reason for that, as we mentioned before, there is some like trade-offs between the performances and the complexity of the chip. And they have different versions that have more of these allowed to work with. But this is the ones that we're working with in our lecture and in lab. And yeah, because if you imagine these interrupts are not like software interrupts, you can just write a bunch of them. They actually require a hard wire to actually connect the peripheral to the core, so the processor. So yeah. And if you look closely on the table here, the first 16 of them are saved for like system exceptions. That those are defined by the ARM architecture. They have an interesting name, an interesting number of negative, which we will learn how to like balance them later. But yeah, that's what the number are referring to. Basically, each of this number here is corresponding to one type of interrupt, essentially. And we have 96 plus 16 of them in the Cortex-M that we're working with. All good? Basically, that number is what we use to look at the table and then figure out where to go to. Okay, so the program state register is one of the special registers before, not part of like the, I think the R0 to R15. This is one of the special registers that holds which interrupts is being fired. It's essentially break into 3 sub-registers. Although if you look closely, they still only take up 32 bits. It's just they nicely reserve different parts so that they kind of become 3 sub-register. The reason for that is for mainly like I believe for like safety reasons, so that you don't accidentally access the wrong register or accidentally change the part that you're not supposed to change, because this is like very critical registers that gives you way back to and holds all the stats, etc. So once you have the interrupt number, we in theory will need to add 16 to them so that they're all nicely positive values instead of some of them become negative. So this is what you will have to do in theory. But again, we work with like a 32-bit system. So in the end, what you're actually going to do is you basically times everything by 4. So whenever there's like an interrupt request going off, and then that number comes in, for example, like number n, and then the address of that pointer or the table to look for in the address in this index table would basically be look at 4 times 16 plus 4 times n, which is 64 plus 4 times n. And for example, if we have like a interrupt request number 7 coming, and then we just do the calculation, and it's going to be 92 or 5C, which is that. And if we have some like negative values, for example here, similarly, we do the whole calculation, and we get 60, which is a 3C, which goes to that one. Any questions on how we find the correct index on this index table, vector table? Okay, perfect. Wow. So let's just put back everything together here. We have the interrupt signals and then corresponding to the interrupt number. Basically, each of the unique signal associated with a unique number, and then these association need allows the NVIC to call the correct ISR or interrupt service routine, the handler functions that does whatever you want it to do. And the location and content of the ISR is defined by you, the programmer. And then if the programmer would do whatever you ask it to do when a certain event is happened. In our case, mainly from the peripherals. Something's been triggered, and then you tell the system or tell other peripherals what to do inside of that ISR, the handler function. Okay, I guess we'll do like a quick review from like peripherals perspective. Basically, there's some GPIO pings goes high. We figure it. For example, this one is a PA.3. This ping goes high, and then we figure out that it's sending an interrupt request, and then a hotwire goes to the NVIC, and it tells that the NVIC figure out it's the wire 9 because it's hotwire. It knows exactly which wire is hot. In this case, it's a number 9, and then we do the calculation, 64 plus 4 times 9, and then we'll figure out when we look at the interrupt vector table to see which, located in the memory, and see which routine, which ISR we should be calling for. And then it turns out we're gonna go to like this function, the RQ handler, the routine handler, and then after that's executed, we go back to the address of previous PC program counter, and then resumes whatever instructions was there. Any questions? Okay, perfect. Okay. So a quick question for you guys, I guess. So the interrupts essentially are like a higher priority function calls that initialized by hardware, by the wire. And then we also know that all those ISRs, those interrupt service routine calls must be like ABI compliant. So I would like you to talk to your neighbors and think, what are the state information that we must be saved for the processor to be resumed back to the original code execution, basically return to the main function or whichever function that was originally in when the interrupt happens. You can refer back to what we did with the previous function calls, but think of like what additional things needs to be stored in this case. Now that's being like a hardware interrupt. Yep. Take some time and talk to your neighbor.
It doesn't really make sense until
My friend says that, oh, I haven't met but my friend says that it's hard to do like
Oh, I think they say it's a spec. Spec is better. Because at the end of the day, let's say it's called right before you oh yeah, maybe 2 is the general. I think 4 is supposed to be let's even check out. Compared to the rest of
Long discussion went on. Sure. All right. A lot of discussion went on. So I'm sure a lot of you wants to share some of your thoughts. Who wants to start first? What do we need to save in this case? Yes.
I was thinking like the registers and the values inside the registers that were used before the interrupt was called.
And which type of registers? Caller, callee, saved?
I was thinking actually like the callee registers because it's like the interrupt, it's like the interrupt handler's like job to like preserve whatever registers were used before. That we can maintain state.
Yes, I think that's like when you're exiting it, you have to make sure those are handled properly. And then, but like when you went into it, like when,
Then it would read that.
yes, exactly. So so those ones are like, I believe like R0 to R3. Those one will be saved as like the caller save registers. So yes.
If the interrupt controller sets the PC, how do you know where it goes there?
If the interrupt sets the PC, how do you know? That's a great question. So we should probably save it somewhere, right? So yes. So PC or like the register 15 is also something that will be saved in this case, as different from the previous subroutine calls. That's also something will be saved. And should we save that in the link register or saving it separately?
No, it should be somewhere else because you don't know what's in there. So like the link register could have something that's useful.
Exactly, because the links register, we don't know exactly where this interrupt happens. It could be in the main program, it could be in one of the subroutines. So chances are the link register is still needed. So both the link register and the PC needs to be saved in this case. So link register is R14, I believe, and then R15. Any other thoughts? Great answers. Every answer is on point. So yes. A stack pointer. And why is that?
Because if the interrupt moves like access to anything in a stack, then when the program, or when it resumes the program, if the program starts stack is also going to be on.
Yes, I think, yeah. And actually stack is where we're gonna save all this stuff into. So the stack pointer will be increased as we push all those stuff inside of the, so yes. the stack pointer will also be in a way stored in this case. Cool. Yeah, I think only thing it's basically the other thing we just talked before, the program state register, which is that thing. So we also happen to store this thing as well because it stores all the interrupt related, like which routine it goes to, etc. So this is also something that we will store. So basically, these are So those are the things we will need to be stored, like the R0 to R3, the link register, the program counter, the program stats register. One more, kind of like a special register, R12. It's also going to be installed. Actually, this register is usually used for intermediate calculations within any of the function calls. We will also store that just in case. But yeah, I think you guys get basically all the stuff on this one. So how we actually do that storing, which is I start stacking and unstacking. Cool. So yeah, this is like a quick float of what's happening. Basically, we have the interrupt signal sending from peripherals or whichever other all-around system, etc. In our case, mostly peripherals, and then it goes to the interrupt handler, and then it figures out what to do. And before that, it first does the stacking, and then after this interrupt handler, like the functions, the subroutine calls, it goes back to the main program, and on that stage, it basically unstacks everything that needed, and this is, on the right, a stack image, which basically at the beginning, it will push down all those registers we mentioned, R0 to R3, and then link register, program counter, etc., R12, because intermediate calculation, and then just push it down. And then whenever it finishes the subroutine calls, finishes the interrupt event, it will basically unstack everything, put it back, and then the program will be back to where it was in the main function or in whichever function it was previously in. I hope this image is quite clear. Yes?
So if you're writing the interrupt function itself, does that mean you don't have to worry about saving the data for you?
Yes, for those registers, yes, exactly. Cool. Yes.
Is it possible to pass values to the ISO? Because you said it's something called pass values. Is that something?
What do you mean by pass values? Agreement, arguments to the? Yeah. They should just exactly. Okay, cool. It's whatever that was saved in the register or the other register you can put in as the argument, which is why we saved the R0 to R3 so that you have the space to put in arguments. Okay, cool. So just to make things a little bit more confusing, but you don't have to worry too much about this. But just to let you know, there are actually two types of stack pointers. One called main stack pointer, one called process stack pointer. The main stack pointer, it's used by default after every reset, and it's usually used for exception handling or other privileged executions. And the process stack pointers usually used for unprivileged or application level tasks. Usually be used in real-time operating systems. Both of them are stored in the same register, the R13 register, and then they have one control signal in the special purpose register to tell to decide which type of stack pointer is using. The MSP or the main stack pointer is mainly primarily used for our class basically, and yeah, just a little bit more detail here. Usually we use MSP, and then in like the thread in the handler mode, we usually use MSP because it's like more privileged. In the thread mode or like the normal program part, which is like the main functions, etc. in your program, we can use both of them. Just decided by the control pin instead of that special purpose register. And yeah, again, in our class, we mainly use the main stack pointer. And since and if you look more closer into like one program, in like one of the program examples, you will see like under the, I'm not sure you can see, oh, it might be too small, but basically it like they have two values stored here, like it's banked as the one each other. One of them is the main, one of them is the PSP. And then if you go to the mode here, it will tells you that, the control here, it will tells you which stack pointer we're currently using. And actually, you might notice that here, the link register is kind of put like a particular, like peculiar value here. And the reason for that is in the event of the interrupt, the linked register also have some other tricks up there. It's a sleeve, which is quite nice. Basically, it's normally used as save the address of the instruction immediately after any of the branch. But in the case of the interrupt, it will indicate whether if it's MSP or the PSP is used, and store the register back when exiting an interrupt. And if you look at the actual value, this is like the table for that. The FFFF9 that we saw, it basically indicates the current, it's going to return to the thread, which means it returns to a function or like the previous main function or types of function that we normally run. And then it also tells you the current stack pointer is the main stack pointer. If it's returned to, like, say, the top one, FFFF1, returns to a handler, that means this interrupt, after it finishes, it returns to another interrupt or return to the next interrupt. Just depends on how you structure or how the priority of these interrupts are. Basically, for that part, you're not jumping back to the main program. All good? Any questions on this? Okay, cool. So yeah, let's go through like an example here. Let's say we have program happening, and then at that point there's some type of interrupt happens at the program counter at 08000044, and then you have to basically, usually you complete the current instruction and then you're running on in order to run the interrupt. There are cases you can break inside of the instructions, but most commonly you finish the current instruction and then goes to the interrupt. It takes very little time. And when this happens, basically, currently the stack pointer points to there, and then we assume the main stack pointer was used for most of our class materials, and then it basically store everything that's relevant to the stack. And you notice that the order was done automatically because in the stack it kind of sorted out for you. And here we have the link register set it to a different value than before because we kind of know, we will know because we will go back to a thread, which is like the main function in this case, and also we're using the main stack pointer instead of the PSP process stack pointer. So now we're inside of the interrupt function, which does something. Here it does some weird stuff, which you probably recognize now. It changes a register that's not supposed to change unless it stores it later. This is like what a bad programmer would do. Hopefully that's none of you guys. And if you need to change any of those like callee saved registers and also needs that, make sure you store, you stack the previous values inside of the register before you do the modification. But in this case, it's a bad programmer, so it does that. It changes the register 4 slightly. But yeah, the program keep on going, and once finished, we look at the LR, the link register, to know that the main stack pointer should be the ones that's be used for unstacking. And then we find where the main stack pointer is, and then unstack everything. And then they go back to the register that previously were there. The only thing that was wrong here is basically the R4, which the callee should have saved it in the stack before it does anything to that register. And then the main program resumes. Any questions on that? Yes.
When the system interrupt handler is storing the special registers, so to say, if it causes a stack overflow exception, does it just terminate the interrupt and go back to the program, or does it just crash?
That's a very good question. Usually it crashes. Yeah. Any other questions? Except you wrote a function to specifically handle that. Like when that exception happens, you wrote a function to do something. Usually it prints out an error message, but yeah, that's. Any other questions? Okay, perfect. So I guess I'll go to the little recap of today's lecture and then give everyone a little bit break. So we talked about like polling and interrupts, and then we talk about the IRQs, the interrupt request. Basically, it's the peripheral sending signals to the NVIC. And then each of these interrupt requests have a number, and the NVIC use that number to look at the pointer to the ISR, the interrupt service routing, instead of the vector table. And then after that, it basically, like the vector table is a list of pointers at the beginning of the memory, just right after the MSP, the 0000. And then after the, when the interrupts triggered, PC program counter is set to the address of that ISR that was being looked up from the vector table. And then hardware will take care of all preserving the processor state by stacking and non-stacking, which is something we just showed. And then it go back to the previous main function as it resumes. Some questions to just put in your head before you go, which happens to be what we're going to talk about in the next lecture. It's the little bit more on the NVIC, the nested vector interrupt controller. Basically, just think about what happens if when there's another interrupt request happening while the program is already handling an interrupt, and how do we set up and control multiple interrupts? And what if we're in some more critical interrupts or more critical part of the code rather than other codes? Anything that we could do to handle this. Yeah. So yeah, that will be today's lecture. Feel free to leave right now and enjoy the remaining of the day.
Good question for you. So, the attendance on Thursday of last week, I thought I left it, but I guess I didn't. I don't know where it went. I've got a photo of my sheet in the class. Yes. Am I all set? Thank you. I also same thing.
Thursday, if there's another worksheet, is there a way we can write it still? Or, because I'm gonna be at a wedding, so. Yeah. Thank you.
So is that just every Thursday, I guess?
We try to make it long, but
Just one more question about the lecture. Why was R12 just saying?
R12, yeah, because that's that register is usually used for all of the intermediate applications. So it's just for like here, between
Okay, alright, thank you. I have 2 questions. Regarding the worksheet, I wasn't aware I was supposed to use it. I often just use my phone. So I was just like, wasn't sure like what I do there.
no worries. I see
Shamil SSHAMELS. My six.
This one?
No, it should be one SHA. Like, yeah. Yeah, my second question is I kind of struggled a bit on assembly and doing labs. Do you know like any sources or like
Assembly for which lab was that?
not I just feel like in general, really. Just I just feel kind of behind with like the assembly language in a way.
Have you taken assembly?
Yeah, I have. And I guess I also struggled then, although I did improve back then, but like I guess it's been a bit of a while, that's fine.
I think 3 material is probably the best one to review.
Right.
But yeah, I think those are probably the best materials.
Gotcha.
Besides that, we will have like some practice exams, so if you can practice,
Yeah, gotcha.
you can come to like open lab hours, etc. to
Yeah.
question.
Yeah. Gotcha, thank you.
Yes, sir.
So in the slide where we were going over how we communicate with the read and write the flip-flops, I was wondering why input only reads 0-bit.
This part?
Yeah. So I understand like so let me just clarify. This comes from the core, right? The write is from the core, right?
Yes.
And then the read is from external.
To the core, which is whatever value you
Oh, okay.
get from these.
Got you. Okay. So I understand if you're writing data, let's say we have a certain instruction, you would want to read the whole bus, whatever, it's stored to flip-flop. So if you're reading, let's say from the pin, you're reading, I don't know, the bit stream of data, right? So why are we only reading 0-bit? And then wouldn't like every clock cycle like overwrite that bit? You wouldn't know what to read at that point? Because you're also reading 32 bits again.
Yes, so for this one, like the 0 there is mainly because it's kind of like how the question is. So because we only ask you to do the functionality on the 0 bits basically 0. This is for like some simplicity.
Okay.
Because if we introduce more, then we have to just take in account like the serial to parallel transactions and how we're gonna take the actual cycles for that, etc. This is just to make it simpler. So that each one of the clock cycle we're able to have some instead of wait the entire This is meaning for the how the question